Today's topic is Bose Einstein statistics. Basic assumptions of Bose Einstein statistics are following. Number 1, this statistics is applicable to those systems in which particles are identical and indistinguishable, and their spin is zero or integer. So this Bose Einstein statistics is applicable for particles which are identical and indistinguishable. We cannot distinguish between them, and their spin is zero or integer. We write spin by s, so it is not r, it is s equal to 0, 1, 2, 3, 4. Those particles which have spin s 0 or integer 0, 1, 2, 3, 4 are known as bosons and obeys Bose-Einstein statistics. These particles are known as bosons. Example: photon, phonon, etc. Photons have spin 1, phonons have spin 2. So these are the particles having integral spin. So these are bosons obeying Bose-Einstein statistics. Number 2, since particles are indistinguishable, we cannot distinguish between these particles. So by exchanging two particles, we do not get new microstates. Number 3, minimum volume of phase cell in phase space is h cube. Minimum volume of phase cell in phase space is h cube. Phase cell is smallest volume element in phase space and it represents a microstate. Its volume is h cube. For quantum statistics, here h is constant, so this volume is constant. H is Planck constant, a constant, so number of phase cells are fixed. Since volume of phase cell in phase space is constant, so number of phase cells in phase space are fixed. And number 4, there is no restriction on number of particles in a phase cell. There may be any number of particles in each phase cell. Now we see distribution law for Bose-Einstein statistics. For this, we consider a system of n identical and indistinguishable particles with spin 0 or integer. For example, black body radiation enclosed in a cavity. Black body radiation enclosed in a cavity, these are group of photons. In radiation, there are large number of photons, which is a group of photons, and photons have spin 1, so these are bosons. We distribute these particles in phase cells, energy states, such that in first cell number of particles are n1 and their energy is E1. total number of particles are capital N, and we distribute these capital N particles in such a way that in first cell number of particles are N1 and their energy is E1. In second cell number of particles are N2 and their energy is E2, and so on, and similarly for other cells. In general, number of particles in ith cell are Ni and their energy is Ei. With this, we consider that there are Gi energy levels in the energy state of energy Ei, that is, degeneracy is Gi. Degeneracy means number of energy levels of same energy. So in ith cell, where energy is Ei, if we have Gi energy levels having same energy Ei, then this Gi, this number Gi, is known as degeneracy for energy Ei. Then thermodynamic probability of this distribution will be given by this formula: W equal to pi I factorial Ni plus Gi minus 1 divided by factorial Ni into factorial Gi minus 1. Here symbol pi I represents the multiplication of different terms. Now we have total number of particles capital N, and we distribute these capital N particles in different energy levels. For ith cell, where energy is Ei, total number of particles are Ni, and these Ni particles are distributed among Gi energy levels. And there is no restriction on number of particles in a energy level. So if we have Ni particles in ith cell and Gi energy levels, if we assume that all Ni particles are in first level, then in denominator we write factorial Ni. Look at this formula for W, thermodynamic probability, which is number of microstates corresponding to this given distribution. In denominator we have factorial Ni. In ith cell, total number of particles are Ni, total levels are Gi. So we assume that Ni particles are in first level out of the Gi levels. So in first level, number of particles are Ni, so we have factorial Ni. In denominator, first term factorial Ni. All particles are in first level. Then the remaining number of levels will be Gi minus 1. Total number of levels are Gi. In first level, we have all these number of particles Ni. So we have first term factorial Ni, and then second factorial is for the remaining empty levels, that are Gi minus 1. And in numerator, we have factorial of sum of these two terms inside the two factorials, Ni plus Gi minus 1. In this way, we can remember this formula for thermodynamic probability W for this given distribution. The symbol pi I represent the multiplication of different terms. We have different terms for I equal to 1, 2, 3, 4. For I equal to 1, we get the first term factorial n1 plus g1 minus 1 upon factorial n1 into factorial g1 minus 1. Similarly, we have other terms for I equal to 2, 3, 4, and this is the multiplication of all these terms. This is the first equation for thermodynamic probability W, equation 1. Now we have two other equations. One is for total number of particles capital N and other is for total energy capital E. Total number of particles capital N will be equal to N1 plus N2 plus N3, and we write it as summation Ni. Summation is for I. And total energy E is equal to summation NiEi. Since N1 particles each have energy E1, so energy of N1 particles is N1E1. For N2 particles each have energy E2, so their energy will be N2E2. So total energy capital E of all the particles will be equal to N1E1 plus N2E2 plus N3E3, and we write it as summation NiEi. So these are the two equations for capital N and capital E. Total number of particles capital N and total energy capital E. These are constants. Total number of particles capital N is constant. Total energy capital E is also constant. These are two equations, equation 2 and equation 3. Now, by taking log on both sides of equation 1, we have log W equal to. This is equation 1 and we take log of this. So left hand side will give log W. For log W we write ln W. Ln W is log W for E base. So log W will be equal to summation I W is equal to pi I, and this term, if we take log, then this pi I will be changed to summation I. Pi I represent multiplication of several terms and this summation represent sum of several terms, addition of several terms. Since log A into B into C is equal to log A plus log B plus log C, if we take log of multiplication of several terms, then this multiplication is changed into plus sign. So this pi I symbol will be changed to summation symbol and log W will become equal to summation I. And now if we take log of this term, in numerator we have factorial Ni plus Gi minus 1. So we have log factorial Ni plus Gi minus 1. Then in denominator we have two terms, and if we take log, then we get with minus sign. So we have minus log factorial Ni and minus log factorial Gi minus 1. So this is log W, and we can neglect 1. 1 appears in this first term and this third term in right hand side. Since Ni and Gi are large numbers, so we can neglect 1 in comparison of Ni and Gi. So we neglect 1 in this first term of right hand side and this last term of right hand side. Then we get log W equal to log factorial Ni plus Gi minus log factorial Ni minus log factorial Gi. And now we use the Stirling formula. Using Stirling formula for higher values of Ni and Gi, Stirling formula is for log factorial n. Log factorial n is equal to n log n minus n. So we use this formula for log factorial n, which is n log n minus n. Then log factorial ni plus gi will becomes ni plus gi log ni plus gi minus ni plus gi. Similarly, for second term, which is minus log factorial ni, we have minus and then log factorial ni will be ni log ni minus ni. Then this will become minus ni log ni plus ni. And similarly, for last term, we have log factorial gi equal to gi log gi minus gi. So minus log factorial gi will be equal to minus gi log gi plus gi. So we used Stirling formula for all these three terms of right hand side. Now we have these two terms minus ni minus gi here, and here we have plus ni and plus gi. So this plus ni and plus gi is cancelled from this minus ni and minus gi, and the remaining terms are summation I ni plus gi log ni plus gi minus ni log ni minus gi log gi. Now we want to find the condition of equilibrium. Equilibrium condition is that for which probability is maximum. It is the most probable state. So for most probable state, W, thermodynamic probability, must be maximum. So W will be maximum or log W will be maximum, and condition that log W is maximum is this, that its differentiation will be equal to 0. From the condition of maxima and minima, differentiation of that quantity must be 0 for its maximum or minimum values. So for most probable state, for equilibrium state, thermodynamic probability W must be maximum, so log W must be maximum, so its differentiation d log W must be 0. So we have d and put the value of log W, which is summation ni plus gi log ni plus gi minus ni log ni minus gi log gi, and this will be equal to 0. Now we differentiate this. D means differentiation. We first differentiation the first term, which is ni plus gi log ni plus gi. We differentiate this by using first and second function. We assume that ni plus gi is first function and log ni plus gi is second function, and differentiate this as first function differentiation of second plus second function differentiation of first. So first function is ni plus gi, and differentiation of first function is ni plus gi. Differentiation of second will be differentiation of log ni plus gi will be 1 upon ni plus gi dni. So correct this. The first term here is written as Ni plus Gi into dNi. So first term will be first function Ni plus Gi, then differentiation of second, which is 1 upon Ni plus Gi dNi. Differentiation of log Ni plus Gi is 1 upon Ni plus Gi, and multiplied by differentiation of Ni plus Gi, which is dNi. So first term will be Ni plus Gi upon Ni plus Gi into dNi. Then we have second function plus second function log Ni plus Gi, and differentiation of first is dNi. Gi is constant here. So differentiation of Ni plus Gi is dNi, differentiation of Gi is 0. Similarly, we differentiate this second term also. First function differentiation of second plus second function differentiation of first. So first function is Ni, second function is log Ni. So first function Ni differentiation of second will be 1 upon Ni dNi. So correct here also, it is minus first function Ni and differentiation of second, that means log Ni. Differentiation of log Ni will be 1 upon Ni dNi. So this term will be minus Ni upon Ni dNi. And then we have minus second function log Ni and differentiation of first is dNi, it is right. And if we differentiate this last term Gi log Gi, its differentiation is 0 because Gi is constant. So correct here in these two terms. In first term we have Ni plus Gi upon Ni plus Gi dNi. So this first term will be equal to dNi only. And correct here also, it is not minus Ni dNi, it is minus Ni upon Ni dNi. So it is minus dNi. So this minus dNi is cancelled by this first term, which is plus dNi, and the remaining terms are log W equal to log Ni plus Gi dNi minus log Ni dNi. Log Ni plus Gi dNi minus log Ni dNi. Put here dNi with log Ni. So this dNi is taken common, and we have log Ni plus Gi minus log Ni into dNi. dNi is in both these two terms, correct. In second term we also have dNi. Then dNi is taken common. Then remaining terms will be log Ni plus Gi minus log Ni, which will be equal to log Ni plus Gi upon Ni, and dNi is common and it is equal to 0. We write this as equation 4. Now we have two more equations from equations 2 and 3. Equation 2 and 3 are for number of particles, total number of particles capital N, and total energy capital E, and these two terms are constants. So since capital N is constant and capital E is constant, if we differentiate these two equations, this differentiation must be 0. So we get two more equations. One is dN, which is equal to summation dNi is equal to 0, and second is for dE. dE will be equal to summation EI dNi, and it will be equal to 0. So we have these two equations also. dN is summation dNi equal to 0, and dE is summation EI dNi is equal to 0. We write these as equations 5 and 6. Now we combined these three equations, equation 4, 5 and 6, by Lagrangian's method of undetermined multiplier. We now combined equations 4, 5 and 6 by using Lagrange's method of undetermined multipliers. For this, we subtract from equation 4 This is equation 4. Log Ni plus Gi upon Ni into dNi. We subtract from this equation the next equation multiplied by alpha, and we subtract the next equation multiplied by beta. So equation 5 is multiplied by alpha. We have summation alpha dni equal to 0, and equation 6 is multiplied by beta. So we have summation beta ei dni is equal to 0. And then we subtract these two equations 5 and 6 from equation 4. From equation 4 we subtract alpha times equation 5 and beta times equation 6. Then in these three terms we have summation in all these three equations, and we have dni common in all these three equations. And then if we subtract from equation 4 alpha multiplied by equation 5 and beta multiplied by equation 6, then we get this equation. Summation dni is common. Then we have log ni plus gi upon ni minus alpha minus beta ei. Alpha and beta are undetermined multipliers which are to be determined. Now this dni does not depend on I, number of cell. Ni is number of particles in ith cell, and di is change in it. Since change in number of particles in each cell is independent of each other, so for each value of the quantity inside the bracket should be equal to 0. So this dni will not be equal to 0, and the quantity inside the bracket must be 0 for each I. So we have log ni plus gi upon ni minus alpha minus beta ei equal to 0, or log ni plus gi upon ni will be equal to alpha plus beta ei. Take exponential on both sides. So we have e to the power log x equal to x. So we get in left hand side ni plus gi upon ni, and in right hand side we have e to the power alpha plus beta ei. Left hand side will become 1 plus gi upon ni, and it is equal to e to the power alpha plus beta ei. Then gi upon ni will be equal to e to the power alpha plus beta ei minus 1. Now revert this, then ni upon gi will be equal to 1 upon e to the power alpha plus beta ei minus 1, which will give the value of ni. Ni is equal to gi upon e to the power alpha plus beta ei minus 1. This is Bose Einstein distribution law. In Maxwell-Boltzmann distribution law, which is classical statistics, we have ni equal to gi upon e to the power alpha plus beta ei. But now here in denominator we have e to the power alpha plus beta ei minus 1. This is the change in two statistics. In Maxwell-Boltzmann statistics and Bose Einstein statistics, this difference is due to this term minus 1. So this is the Bose Einstein distribution law. Ni is equal to gi upon e to the power alpha plus beta ei minus 1. Now we consider the difference in classical and quantum statistics. In classical statistics, particles are identical and distinguishable. So by exchanging two particles we get new microstate. And example is particles of gas molecules. In quantum statistics, particles are identical and indistinguishable. So by exchanging two particles we get new by exchanging two particles we do not get any new microstate. Correct this? It is not we get new microstate, it is we do not get new microstate. When particles are distinguishable, then by interchanging two particles we get new microstate. But when particles are indistinguishable, as in quantum statistics, then by interchanging two particles we do not get any new microstate. Example of quantum statistics are photons, electrons. Photons are bosons having spin integral spin, and electrons are fermions having half spin, and this will obey Fermi-Dirac statistics, which is also quantum statistics. In classical statistics, volume of phase cell in phase space is h0 cube. h0 is arbitrary constant which we can choose as small as possible. So we can increase number of phase cells as we want. But in quantum statistics, volume of phase cell in phase space is h cube, which is constant because h is constant, which is Planck constant. So number of phase cells are fixed in quantum statistics. These are the differences between classical statistics and quantum statistics. Classical statistics is Maxwell-Boltzmann statistics, and quantum statistics are two. One is Bose Einstein statistics and other is Fermi-Dirac statistics. Bose Einstein statistics is for zero or integral spin particles that are bosons, and Fermi-Dirac statistics is for half odd multiple spin particles that are known as fermions.